Welcome to the second installment of quantum mechanics. Last time we learned about the photoelectric effect. You shine electrons on some metal, you shine light on a metal, it ejects electrons. We can measure the energy of those electrons by looking at stopping potential. Classically, we expected to see electrons with a wide range of energies, including some at very, very high energies. But that's not what they found. What they found was that there's a certain maximum kinetic energy. First weird result. Second weird result, you did not increase that maximum kinetic energy by using brighter light. You just got more electrons, but the energy of each electron was the same. You could increase the energy of each electron by using light at a higher frequency, blue light instead of red light. And none of that can be explained by classical physics. So the question is, what does that mean? Remember, the graph of stopping potential, meaning kinetic energy, versus frequency is linear. And so it has a slope equal to h, and that value is 6.626 times 10 to the minus 34 joule seconds. We'll just call it h for now. And the intercept we can interpret as phi, the work function. And so the graph of that turns into maximum kinetic energy equals hf minus phi. H is something called Planck's constant. Its value is 6.626 times 10 to the negative 34 joule seconds. Or if we want to use units of electron volts for energy, which is usually more convenient, 4.14 times 10 to the minus 15 EVS. And phi is the work function, the amount of energy that it takes to break an electron loose. So hf is the amount of energy it gets from the light. Subtract the amount of energy required to break it loose, and you have how much kinetic energy it has. And the other thing is, and the way we explain this is that light can only carry energy in discrete amounts. We call the discrete amount a photon, and we say that the energy of a photon is proportional to its frequency. So the higher the frequency of the light is, the larger each photon is. The idea is that each electron can only get hit by one photon, and that photon gives all of its energy to that one electron. So that's why there's a maximum kinetic energy. Each photon has the same amount of energy. So no electron can possibly get more energy than that. It also explains why the maximum kinetic energy of the electrons goes up with frequency. Because if a high frequency photon has more energy than a low frequency photon, then the electron that gets hit by the high frequency one will come out with more kinetic energy than the one that got hit by the low frequency. So that is how we explain all that. And that's very, very important. Light carries energy in discrete amounts. The amount of energy in that discrete amount of energy is proportional to the frequency. But it is really weird. It is not at all what classical physics predicts. And because of that, if the photoelectric effect had been the only experiment that demonstrated this, the idea of quantum mechanics probably would have never gained currency. It would have just been another weird idea that happens to explain one experiment. But there was another reason why it was accepted among physicists. And that has to do with the Blackbody spectrum. Remember when we were talking about global warming, we mentioned that the sun is a black body, and anything else that is heated to a finite temperature will emit light. If you plot the energy emitted versus wavelength, so it emits light of all wavelengths, then the graph we get looks like that. It has a peak at location lambda max, which depends on temperature, and then it trails off here, and it goes to zero at short wavelengths as well. Now, if you work with classical statistical physics, and it requires considerably more math than we know at this point, but if you do those calculations, you'll find that classically, we'd predict the spectrum of a black body. It follows very, very closely on the long wavelength side, but then instead of a peak, it just keeps going up and has a vertical asymptote. which is bad, because it predicts, among other things, that you get an infinite amount of energy radiated from something at a finite temperature. And it's obviously highly divergent from observations. Observations say there's not a whole lot of ultraviolet light emitted by something at low temperature. The classical prediction is there should be a ton of ultraviolet light being emitted from everything, even very cold stuff. Because of the discrepancy between theory and experiment was most pronounced in the ultraviolet region, this is called the ultraviolet catastrophe, which would be a great name for a band. And physicists had known this for 20, 30 years before anyone came up with a good theoretical explanation for the peak. So this is classical theory, and the blue is experiment. But then around 1880 or so, German physicist Max Planck came up with an idea that would explain the experimental results. He said, if light carries energy in discrete amounts, and that the amount is proportional to the frequency, we can explain the shape of the blackbody spectrum. And no one really paid too much attention to that, including Planck, who was convinced that light doesn't actually carry energies in discrete amounts, but it was just a mathematical explanation for something else and probably less interesting that was going on. However, about the same time Planck did this, Millikan did his experiment with the photoelectric effect. At the time, no one connected the two phenomena. But in 1905, a physicist that no one had heard of at that point noticed that the value of h that Planck used turned out to be exactly the same as the slope of the graph that Millikan made. H equals 6.626 times 10 to the negative 34 joule seconds. And this unknown physicist said, oh, Planck's hypothesis that light carries discrete amounts of energy can be used to explain Millikan's experiment. So the same idea used to explain two very different and very interesting experimental results. That is probably not a coincidence, and that was what convinced most physicists that quantum mechanics is real. That young physicist, who no one had heard of, that was Albert Einstein. He was 26. Get working. You have 8 years. And that was the paper that he won the Nobel Prize for. He did not win a Nobel Prize for his work in relativity. He won it for quantum mechanics. He probably should have won one for relativity too. But oh well. Now we've got to do some examples, the slightly boring part. But you'll be asked these sorts of questions on the test, so we've got to do them. Here's this example. When we have light of wavelength 450 nanometers is incident on a metal plate, stopping voltage is 2.6 volts. Find the work function of the metal. Okay. So if the stopping voltage is 2.6 volts, that means the maximum kinetic energy is 2.6 electron volts, because that's a unit of energy that's equal to the amount of energy you get when you put an electron through a potential difference of 2.6 volts. So Kmax is 2.6 electron volts. The light, we're given wavelength, we want to convert that to frequency. Remember, frequency equals c over lambda, where c is the speed of light, 3 times 10 to the 8th meters per second, and lambda is 450 nanometers, or 4.5 times 10 to the minus 7 meters. Grab a calculator. And we get 6.67 times 10 to the 14 hertz. we're going to use the idea that the maximum kinetic energy equals the photon energy hf minus the work function phi, and solve for phi. So that means phi equals hf minus k max. Plug in numbers. We're using electron volts, so we're going to use this value of h, 4.14 times 10 to the minus 15 joule seconds, times the frequency, minus that maximum kinetic energy, which is 2.6 electron volts. Again, we put this in our calculator. Oh, did it wrong. And we get a work function of 0.16 electron volts. Pretty easy problem. Main thing is to keep your units on track. If you want to use joules, you have to use one value of h. If you want to use electron volts, which is usually more convenient, you want to use another value of h. Now part B. Find the longest wavelength of light that will produce photoelectrons. So that means Kmax is equal to 0. You're giving the electrons just barely enough energy to escape from the surface and no more. And so that means that the work function equals the amount of energy carried by the photon. We know the work function. We're looking for the wavelength, so that means we need to change that to frequency to c over lambda. Solve for lambda gives us phi equals hc divided by the work function. Our work function is given in electron volts, so we're going to use the value of h that has electron volts. Speed of light, 3 times 10 to the 8th meters per second. And phi, 0.16 eV. And the value, and this maximum wavelength is 7.7 times 10 to the negative 6 meters, or 7,700 nanometers, which is the more usual way of expressing it. That's a pretty long wavelength, because that's a very, very small work function. Okay, and last, we want to find the energy of the emitted photoelectrons if the wavelength of light is 520 nanometers. So in this case, we're looking for Kmax equals the photon energy minus the work function. Once again, we're given a wavelength, so we use hc over lambda. 4.14 times 10 to the minus 15 electron volt seconds times 3 times 10 to the 8th meters per second, the speed of light, divided by the wavelength, 5.2 times 10 to the negative 7 meters, and then we have to subtract 0.16 electron volts from that. Put this in the calculator. And sometimes the calculator hates you. And we get the photon energy, or the electron energy, to be 2.2 electron volts. And that makes sense, because the longer wavelength light is going to be at a lower frequency, and so it won't give as much energy to the electron, and therefore this 2.2 is less than the 2.6 that we had with the shorter wavelength light. Now here is some practice for you. Find the energy of the electrons emitted from zinc, gives you the work function, when light of wavelength 410 nanometers is shined on it. The answer you should get is 1.33 electron volts. Make sure you can get that answer. Also, you might think about how you can get monochromatic light with technology available in 1890 when Millikan did the experiment. That means no lasers and no LEDs. And that brings us to the end of the photoelectric effect. Come back for our next installment of quantum mechanics.